All right. Welcome to our first lecture for Chapter 7. To follow along with this and to really get the most out of it, it'd really be helpful if you take a minute and get a periodic table, book, paper, periodic table, whatever you want to get. Periodic table is going to help a lot because Chapter 8 talks about periodic relationships. So we're going to be talking about elements, how they're similar, how they're different, how their electrons are configured, and so if you have a periodic table, that's really going to be pretty useful for you. So let's get into it. This is just a kind of a cool little graph. It tells us when the different elements were discovered. Not something you have to commit to memory, but just to kind of give you an idea. Ancient times, you got a few metals in here: iron, copper, silver, that kind of stuff. Gold, mercury, these have been around. Carbon and sulfur for a really long time, and we've known they've been around for a really long time. Genesis mentions gold, that there's land where the gold is good, so it gives us this idea that we've known about gold for a really, 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 really long time. Middle Ages, up to the 1700s, we got a few more elements, not a ton, but a few more. 1735 to 1843, the field of chemistry kind of explodes. You can see a lot of that sort of weird purple color is scattered throughout here, unless you're colorblind or red-green color deficient, in which case this table is going to be a little weird. But hopefully you can see that. 1843, we add a few more: gallium, germanium, indium, those kinds of guys. 1849, we pretty much get all of our noble gases figured out, just in one quick run there. And then 1923, sort of a weird color here, but it fills in a few of these guys: 72, 75, 43, something along those lines. And then 1965 to present, basically we start making things, firing protons in to try to make little elements that exist for just a second or so we can give them some sort of odd name and be famous. And so that's where we find these elements historically. So here's the useful tidbit to this chapter's ground state electron configurations, which means where are electrons. Here you can see hydrogen, lithium, sodium, potassium. Hopefully remember these are alkali metals, and they are 1s1, 2s1, 3s1, 4s1, so it's nice because these are all s1. And then of course their coefficients go for 1 going across, 2 going across a period, 3 going across a period, 4 going across a period, 5, on and on and on. If we move over here, it's S2, 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 and so this is nice because this lets us know exactly how many electrons we're dealing with and where they are. And you can see it's kind of the similar trends over here with P's and D's, and so it's pretty useful for us. So we call that the NS1, N being your principal energy level, 1, 2, 3, 4, 4s1, 5s1, that kind of stuff. This would be NS2, so whatever your principal energy level is, and then followed by S2. This is a 2s2, a 3s2, a 4s2. Here we have an NS2 NP1, so we know our valence electrons are going to be around 3 valence electrons. So here's 3s2, P1, 4s2, P1, 5s2, P1, and on and on and on it goes. So we know they've all got a very similar electron configuration. Here NS2 NP2, so 4 valence electrons for carbon and silicon. Here NS2 NP3. We're getting a little closer to that whole filling the octet idea. Here we're at 5. So you're going to get some guys in here that can form some pretty weird bonds, but they are going to want to try to get to that 8 if they can. Here with oxygen and sulfur we have NS2 NP4. So here the second one, 2s2 2p4. In the third period it's 3s2 3p4. Fourth period 4s2 4p4. So they're all going to follow that, where N remains our principal energy level. And then here we get to a pretty reactive group we call the halogens, and you can see why they're so reactive. NS2 NP5, 2 and 5 puts us at 7. Generally we want to fulfill an octet rule, so they're very, very close to fulfilling that octet rule. They're just 1 electron away, but they do follow that same set: 2s2 2p5, 3s2 3p5, 4s2 4p5. So it's nice because they're predictable. It's one of the nice things about periodicity. It's one of the nice things about this chapter. then we get to our noble gases. Helium, neon, argon, krypton, the guys that don't particularly care to bond with anybody else, because here they sit at Ns2np6. 2 and 6 is 8. They've got a stable octet. They're about as stable as you can get. So bear in mind that helium doesn't quite follow this, the whole stable octet idea, because it has 2 electrons, so it fills the s orbital and it's good to go. But for the rest of them, 2s2, 2p6, 3s2, 3p6, and on and on and on it goes. So that's the stuff we're kind of familiar with. Transition metals gets a little weird. We get D1, D2, D3, and you're like, yeah, I'm tracking this. D5, and some D4, and some D5, and it kind of starts to get a little weirder. Some D6, some D7, some D8, they're kind of all mixed in there. Some D9s and 10s and 8s all mixed in, and transition metals, right? And then D10. So, okay, we can at least say D block. This is the D block. That's about it. There's some 4F, there's some 5F, and that's kind of how we can break out this whole periodic table into something useful. Here's representative elements. That's our alkali metals, our alkali earth metals, our transition metals, those weird little things we just talked about. Zinc, cadmium, and mercury, the end of our transition metals, kind of moving into our metalloids, which is this little stair-step doodad here. And then some more representative elements that we can really get. You know, this is going to be a -1, this is going to be a -2. We know their electron configuration, that kind of stuff. Lanthanide series, green right here, actinide series, pink right here, and you're probably already familiar with that. So let's look at electron configurations. For electron configurations, we got to remember that whole drawing of that triangle for, you start with 1s1, or rather 1s2, 2s2, 2p6, 3s1. Remember drawing that all the way up to 7, and on and on and on you fill. Well, hopefully you also remember noble gas shorthand. Here for sodium, if you look in your periodic table, sodium needs to get to a number of electrons. If it's not in a cation or an anion or anything like that, sodium needs to get to 11. And so we can either name that with this long chain that goes, 1s2, 2s2, 2p6, 3s2, or rather 3s1, and we'd be done. We could write all of those, or we can go to the noble gas that's 1 period above sodium. Write the noble gas in brackets, just write 3s1, and you're done. So that's a lot shorter way to do it. Will kind of save you a headache. So if you had the Na+, the ion form, well, plus means we've lost 1 electron, and if we've lost 1 electron, then we're now getting rid of the 3s1 electron, and you can just write sodium's electron configuration as just neon in brackets. So it's really even easier. If you don't remember how to do those, come see me, because you're going to want to know how to do these. If you looked at calcium on your periodic table, you'd see that now we're kind of in the alkali earth area. You should be looking at about 20 electrons, and so we could either write that out as a really long 1s2, 2s2, etc., 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 or we can go 1 period above calcium, find the noble gas, which would be argon, put it in brackets, and since calcium's in the second group, we know it's a S2, so we just find how many periods down it is, which is 4. It's second group, 4s2, and we're done. So then the calcium ion, 2+, which is, calcium being rather stable, is we get rid of those 2 electrons, and calcium's now taken just the shorthand notation of argon. So hopefully you're realizing the reason we're forming cations is to gain noble gas configuration. Noble gases are incredibly stable. Atoms would like to become so they lose electrons to gain stability like a noble gas. So keep an eye out for that trend, because you're going to see it a lot. Aluminum, same story. Alright, so, there you go, that's nice. Atoms lose electrons, so that the cation has a noble gas outer electron configuration. Same thing we just talked about. So, hydrogen, 1s1, how does it become more stable? Well, it could lose 1, it could gain 1. If you lose 1, it'd be kind of odd, but if we gain 1, we're 1s2, and we're like helium. And helium is a noble gas, so that's how hydrogen can become stable. Fluorine, what do we have here? 1s2, 2s2, 2p5. We find ourselves pretty close to stable. In that outer shell, this is an inner electrons, but the outer level would be 2, principal energy level, and that's currently at 2 plus 5 is 7, so we're close to stable. If we could get that to be 2p6, we'd be in really good shape, and that's why most often when you find fluorine, it's got that negative charge, the fluoride ion. Now we're at 8 on the outer shell, and we are configured like neon. We're in a good shape. So oxygen, same story. We're at 2. In the 2 level, we're at 6. If we can gain 2, we'd be at 8. We'd be at noble gas configuration. So a lot of times you see O2 minus for this exact reason, because it gives it the same electron configuration as neon. Stable, stable, stable. We like stability. Nitrogen's got a little further to go. We've got 2 plus 3 is 5 in that outer level. So we really need to either lose 5 or gain 3. Probably going to be easier to gain 3. And so more often than not, you see nitrogen is a 3 minus. Again, it gets it to neon. So atoms gain electrons, so their anion has a noble gas outer configuration. Same reason. If you're on the left side of the periodic table, probably going to be easier to lose a couple electrons. If you're on the right side of the periodic table, probably going to be easier to gain an electron or 2. And so those are the ways we become stable. So here's your cations and anions. Again, very similar chart. All these guys in the first group, they're going to form +1 cation. These guys here, +2 cation. These guys over here, more often than not, +3 cation. These guys over here, -1 cation. They gain 1, they go over here. Oxygen, sulfur, probably a -2. These over here, probably a -3. These guys over here, tough call. I mean, you're in the middle. What are you going to do? Lose 4, gain 4, share? A lot of times they share. Carbon, this super flexible backbone that makes up organic chemistry. Do we give 4 away? Do we gain 4? Well, let's just share and be a little more flexible about this. That's kind of carbon's strategy for that. So to be isoelectric, iso means same, and so to be isoelectronic means to have the same electric. So for chemistry, that's the same electrons, the same number of electrons. So if you have the same number of electrons, you have the same ground state configuration. So how do we get the same number of electrons? Well, to become stable. If we have sodium and it loses an electron, it has the same number as neon. If we have aluminum and it loses 3 electrons, it gets the same number as neon. They're becoming stable. And to become stable, they're becoming like the same noble gas. Fluorine, if it gains 1, also becomes like neon. Oxygen gaining 2 becomes like neon. Nitrogen gaining 3 becomes like neon. And so what we can say is that sodium plus, you can't just say sodium. You gotta let them know it's the cation or anion. Aluminum, cation. Fluorine, anion. Oxygen, anion. Nitrogen, anion are all isoelectronic with neon. Okay? Their stable forms are isoelectronic with neon. They have the same ground state electron configuration. So what neutral atom is isoelectronic with H minus? Take a minute and think about it. Alright, you figured out? If hydrogen starts off with 1 electron, hydrogen minus has a negative charge, so it must have gained another electron. So that means H minus has 2 electrons. It's 1s2. Well, what element has 2 electrons? Helium. So 1s2 is the same electron configuration as helium. So if we look at transition metals do tend to form cations. So when a cation is formed from an atom of a transition metal, electrons are always removed first from the n orbital, ns orbital, and then we remove them from the d orbitals. Now I wish there was an easy way to explain this, but it's not as simple as I wish it was. When we fill electrons into orbitals, when we're kind of mapping these out, the 4s2 electrons are more stable, lower energy, so we fill those first. Then we go through and fill 3d6, up arrow, up arrow, up arrow, down arrow, down arrow, down arrow, that kind of stuff. So you'd think, well, when we take them off, we'll probably take off the 3d6. They're, probably the least stable. But really, because these are principal energy levels, 3 is going to be closer to our nucleus than 4. And 3D, D is more stable than S. And so to keep this iron atom as stable as it can possibly be when it becomes the iron cation, we always remove electrons from that s orbital. At least we start there. If we have to remove more, we remove them from the s orbital, then we go ahead and we remove them from the d orbital. Now, that's for transition metals, so don't get too excited about that for the whole periodic table. Transition metals, all right? So to make that the 2+, if you had to write the electron configuration, you had to become 2+, you had to lose 2 electrons. We know we have to start at ns, so this is our ns. When we lose those 2, it's 4s0. You don't write something if there's 0 of that something. So you'd have to write it like this: argon 3d6, dropping the 4s. So kind of an odd idea. If we did 3+, we got to follow that same rule. Start at the ns, drop 2. Now the ns is gone. Now we move to 3d, and we've got to get 3+. We've lost 2, we need to lose 1 more. So we take it from 3d6 to 3d5, and we write argon 3d5 with 4s being gone. So kind of a tricky thing, not too bad, but here's manganese without a charge currently, just argon 4s2 3d5. That's how you would complete manganese. And then if we wanted to make it a 2+, drop them from the ns orbital first and just write it as 3d5, and that's pretty much that. So we're going to talk about some periodic trends that we see when you get these elements all lined up in the periodic table. You do see repeating trends. They're not perfect, all of them, but they are, the general trend. Things like effective nuclear charge, atomic radius, ionization energy. If you took Gen Chem with me, hopefully this all sounds really familiar. But we're going to start with kind of a tricky one. It's the idea of effective nuclear charge. And effective nuclear charge is basically the pull that an electron feels from the nucleus. Okay, so you can think of them like a magnet. Nucleus is maybe, let's say, the positive end of one magnet, electrons the negative end of the other magnet, and they're going to be pulled together. So the pull that the positive magnet puts on the negative, that's effective nuclear charge. So here's your formula for it. Effective nuclear charge, ZF, is equal to Z minus sigma. Now sigma is a shielding constant. I'll have to look, but I don't think we're going to do a whole lot of math with the shielding constant. They approximate it this way for us. The effective nuclear charge is about equal to Z minus the number of inner core electrons. And so here they kind of break it down for us. Go ahead and grab your periodic table. Look at these guys: sodium, magnesium, aluminum, and silicon. If you look at them, you're going across a period here. That's why it's 11 electrons, 12 electrons, 13 electrons, 14 electrons. So again, you got to think about it. What's it mean to have 11 electrons? Well, it means we got 1s2, we got 2s2, we got 2p6, we got 3s1. And so for our core, that takes us up to that whole 2p6 range for 10. Then 2 is full, and we move to 3. So we've really only got like 1 extra electron hanging out here, and that whole 2p6 business gets us to 10. And so for all of these, you could say your core is 10. That 2p6 and that stable octet there is 10, 10, 10. All of these have that. But the excess over that octet, this has 1 electron extra. This has 2 electrons extra, this has 3 electrons extra, and this has 4 electrons extra. And so their effective nuclear charge becomes this Z, their total number of electrons, minus their core electrons. So our effective nuclear charge here would be 1, 2, 3, and 4. So you could say this guy has a little bit of a stronger pull on its electrons than sodium does. And so let's look at how that changes our radius. Here, our radius is 186, and if this guy has a stronger pull on electrons than this guy, you would expect the electron cloud in silicon to be shrunk, pulled in tighter than the electron cloud about sodium. And sure enough, that's what we see. Here's our radius of the electron cloud in picometers. Sodium's about 186, magnesium a little bit smaller, aluminum a little bit smaller, silicon a little bit smaller. And so as we add more electrons, that effective nuclear charge is going to increase a little bit, and it's going to pull those electrons in tighter and tighter. So I said it was a trend. What's a trend look like? As you progress down a group or family, you're going to be increasing that effective nuclear charge. Adding more electrons, adding more electrons, adding more electrons, adding more electrons, we're increasing that charge. Bear in mind, as you move down, you're also adding protons. So it's like we're adding more negative magnets, we're adding more positive magnets, we're pulling each other in tighter. Now as you move across a period, add protons and electrons, add protons and electrons, add protons and electrons, on and on and on and on and on. We add protons and electrons, then we're going to increase that effective nuclear charge. Now we've talked a little bit about electronegativity in this course, and I'm not trying to say you can definitely relate these two together all the time, because that's really not the case. But as we look at this trend here, where we see that effective nuclear charge increasing as you move across, remember that fluorine is kind of the biggest, greediest dude around who really wants electrons. So it's not that surprising to see this trend going this way, where the effective nuclear charge, or the pull those electrons feel, would be stronger over here by fluorine and oxygen, when we already are kind of familiar with them as being rather greedy. Now, you can't necessarily make that correlation with them increasing effective nuclear charge down a group, but we can kind of make that connection as we change effective nuclear charge going across the period on the periodic table. So that's something to kind of think about. So we'll stop there for now. We'll pick up atomic radius next time, but this will be enough to get us started. So thank you.